and what is random variable. And in last class we have discussed what is random processes. So now, like we have in the case of random variable, we are calculating mean, variance, covariance, standard deviation. So like this in random processes also, we calculate their mean function, mean of the random process, covariance, auto covariance if we are having same random process, and if we are having more than one random process, then we have cross covariance. So like this kind of terminology we will learn. So like in, we have to first because if we want to calculate this mean, variance, and other terms, we require this what we call this random process xt belongs to g. We have to define its density function or distribution function also. So density function like this fxxt, and distribution like capital F x t naught t. So here we consider this xt as a random process, and for any t naught belongs to j, xt naught is a random variable. Wait a minute. So here this xt is the random process for any t belongs to the j, where j is the index of time. It may be discrete or continuous. Like j may be interval like 0, 1 or a comma b, or it may be like discrete numbers like set of natural number 1, 2, 3, 4, n, or set of integer like minus infinity, then dot 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 minus 3, minus 2, minus 1, 0, 1, 2 up to infinity. So first we define its density for the distribution function, and the distribution function like cumulative distribution function. And if you remember the earlier classes, this distribution function is denoted by capital F. So here capital F is denoting the distribution function. And here we are writing this random variable. So when we know that for any particular t naught, that is when time t is fixed, we can this x t naught becomes a random variable. So x t naught is a random variable, and we are trying to calculate its cumulative distribution function fx t naught x, which is actually, if you remember the earlier definition, it is probability that x t naught less than equal to x. Here you can see the earlier definition. When x is a random variable, its distribution function is defined by this fxx, probability that x less than equal to x. In particular, if we are having random process, in random process, when the time t is fixed with some value t naught, then the probability of x t naught is less than equal to x, gives us the value of the distribution function at the point x. Now, if t1 and t2 are two different instants of time, and that means xt1 is a one random variable and xt2 is another random variable. And if we are having more than one random variable, then we have a concept of joint distribution function, joint density function, joint probability mass function. So we have to here define this joint cumulative distribution function, that is this one. So earlier it is also like fxy, x comma y, but here the random process is capital xt, and for the specific time points t1 and t2, we have different variable, like xt1 is one variable, xt2 is another variable. And this x1 is also a variable. X1 is moving from minus infinity to plus infinity on the real line. Similarly, this x2 is also moving from minus infinity to plus infinity on the real line. So this is the way we represent the joint distribution function of the two random variable xt1 and xt2, and defined like earlier. Xt1 is less than equal to x1, comma xt2 is less than equal to x2. So here comma, you know that this comma is representing the intersection of these two events. In more generally, if you are taking more than two instance of time, like we are taking n instance of time, t1, t2, tn, and then we want to calculate the joint cumulative distribution function of these n random variable. Here each x1 is moving from minus infinity to plus infinity. Then it is defined as the intersection of the probability of the intersection of all these events. So this is the way we define our cumulative distribution function, or simply distribution function. And the more other concept is also generalized like this. So like how you write probability density function, the differentiation of this distribution function is known as the probability density function. So the same concepts are generalized for two random variable, and in case of xt1, xt2, xtn also in case of n random variable. So see this example. So here in previous you can see that xt is representing here and t belongs to j. And I told you that in this book, if we write xt, it's mainly it is talking about the continuous time process. And here he thinks that, or he assumes that j is a continuous, but it can be used for both also. X t and t belongs to j, where j is also like a discrete set. That can that case also it can we can use this one. But for specific, like if you want to write for this discrete time random process, so we specifically write xn. So here if I write xn, it my meaning is like that xn, such that this n belongs to the set j, and j is this 0, 1, 2 up to infinity. So instead of writing this n above, I write n in the suffix, and you understood that this is a discrete time random process where n is moving from 0, 1, 2 up to infinity. So this is the information given here. So by looking at the random process, we can say that it is discrete or continuous. So as here I am taking a discrete kind of value, so it's a discrete time random process. Now here we are saying that xi's are IID, standard normal random variable. So here IID stands for independent identically distributed random variable. So independent means if you take any xi and xj, then xi and xj are independent. It means covariance of xi and xj when j is not equal to I is 0. And identically distributed means they follow all of them, that is all xi's where I belong going to 0 to up to infinity follow the same distribution. In particular, in this example, they were following standard normal random distribution. So here first we have to write down what is the density function of the xn for all n, and what is the joint density function of xm and xn when n is not equal to n. So as it is given in the question that xi's are standard normal random variable. Standard normal variable means xi's are following this n01, that is mean 0, and variance 1, that is this xn n01. And you know that this its density function is this one, f of x n x equals to 1 upon root 2 pi e raised to power minus x square by 2. Now, if m is not equal to n, xm and xn are independent because it is given that xi's are IID. So when m is not equal to n, it means xm and xn are independent, and we have to calculate their joint density function. The joint density function is noted by this f xm xn x1 comma x2. As they are independent, so their joint density is actually product of their density functions. So it is fxm x1, fxl x2. Now in this formula, we replace once small x by x1, we will get the density function of xm x1, and to if we replace x by x2, then we will get fxn x2. And after simplification, this is the joint density function of x1, xn, and xn. Now, once we define this joint density and distribution function, then it means that we are in position to calculate mean. So the mean of the random process is defined by this, that this is a random process, xtt belongs to j. Then, and we are defining this definition for all discrete or continuous. We are not, this the same definition will work. So if xtt belongs to j, the mean function is denoted by mu xt from the time set to the set of real number is mu xt, that is expectation of xt. Earlier it is also expectation of x mean, but since here the time is involved, so this mean is also a function of time. So the expectation of the random process xt is said to be a mean function here, and it is mu denoted by mu suffix capital xt and defined by expectation of xt. Similarly, for the case of discrete, we can write like this, like you can see in the mu xn equals to expectation of xn. So this is the way we denote. So because here we are assuming that j is a discrete set. So it's a, for discrete time random process, the mean function is denoted by mu xn, that is expectation of xn. And for continuous time is this one, even though this can be used in the both the case, but you have to understanding what is t. That means you have either you have to, if it is continuous, then you have to, and then like this. Then, so there is one problem. So in last class, we have already discussed that you have $1,000 and this is the interest rate, and you are using compounded interest formula. And the value of xn is given by this. Xn equals to 1000, 1 plus r raised to power n goes to 0, 1 to infinity. And the value of r is having randomness, and r is following this uniform 0.04 to 0.05. It means r is a uniformly distributed random variable. Then we have to calculate its mean function. So we know that the mean function is defined by mu xn, that is expectation of xn, and then expectation of xn, like if you remember this, expectation of xn, and that is expectation of 1000, 1 plus r raised to power n. Or you can directly, if you don't want to follow this one, you can directly write, because you know that r is a uniform. So its density function is like 1 upon 0.05 minus 0.04. That means 100, because in the denominator we are getting 0.01. It means, and it's a continuous type also. So this expectation can be directly written as like this. So I'm writing here integration 1000 1 plus small r raised to power n, and then you have to multiply the density function. Density function is 1 upon 0.01 and dr, and the limits of the integration is 0.05 from 0.04. So like this you can do integration and you will get the same result. Okay, or you follow the procedure given here, like you write 1 plus r as y, as r is uniform 0.04 to 0.05, so you can 1 plus r is obviously uniform 1.04 to 1.05, and for this case the distribute you have to calculate this what we call it density function of y, and the density function of y in that case is 1 upon 0.01, and where y belongs to 1.04 to 1.05, and then you will get this and then this. So like this you do and you will get the mean function. So here you can see that this mean function is a function of time. So like for different n you have different values. So that is the expected value is different. The expected outcome is different for different values of n. Then here we have a problem of continuous kind of random variable. We can see here this is actually continuous. So by looking at the random process, you can say it is continuous or discrete time. So here you can see that this time is belonging to certain interval 0 to infinity. It means it's a continuous time random process, and it is defined by this xt equals to a plus bt, where t belongs to 0 to infinity, and it is given that a and b are independent and normally distributed with mean 1 and variance is also 1. So now for this process, you have to find its mean function. You know that mu xt is actually expectation of xt. This is the definition. And here xt is actually a plus bt. So like this we have to write, and then we have to distribute e over each term. It's like that. It will not have any effect on t because t is a real constant. So this t will be the outside of this expectation. And then what is the value of expectation of a? So it is given in the question that A and B are independent and normal 1 1. So normal 1 1 means that the mean of A is also 1 and the mean of B is also 1. So this expectation of A is given 1 and expectation of B is also given 1. So it is the mean function of this random process, that is mu xt is equals to 1 plus t. Then we discuss the concept of autocorrelation and autocovariance. So when we use auto words, it means we are talking about the same random process, and that is only one random process is there. If we are talking about cross correlation or cross variance, then it means we are having two random processes. So auto stands for single random process xt. So the mean function gives us the expected value of xt at any time. So if we want to know, like for two different instants of time t1 and t2, xt1 and xt2 are two different values of xt and how they are related, because xt1 is one random variable and xt2 is another random variable. Either they positively correlated or negatively correlated. It means either increasing of one increase the other also, or increasing of one decrease also, or they are having not effect on each other. It means their covariance is zero. So like this we have. So first we define this for any. So this is the general formula. Like if it's a discrete, then here xn or xn. Okay, t1 is replaced by n and t2 is replaced by n. So this is the definition of autocorrelation function. Okay, you have to remember this autocorrelation word, and it is always denoted by this Rx. It means Rx single process is there, and T1 and T2 are two different instant of time for which we are having two different random variable xt1 and xt2, and the expectation of this product is known as the autocorrelation function. Now we calculate what is the autocovariance. So autocovariance is Rxt1T2, that is this one, minus mean of function of xt1 and mean function of x at t2. So this is the autocovariance. So better to remember this one, autocorrelation and autocovariance, because there are other terms also when we have more than one random process. So this is the, you know how to calculate expectation. Just if we calculate, we are having two instant of time t1 and t2, then expectation of xt1 into this, sorry, expectation of xt1 into xt2 is known as the autocorrelation function, and this. And you know that actually it's a covariance kind of term. Na? In covariance, what we are having, if you remember, covariance is like expectation of xy minus expectation of x minus into expectation of y. So it's like that. Because expectation of x is mean, so mean mu x t1, mu x t2. Because mu xt is a mean function of the process, and in particular when t equal to t1, it means it's a mean of the xt1 and mean of the x t2. So like this, we define our this autocorrelation and autocovariance function. So like with the help of this autocorrelation function, we can calculate the expectation of xt square also. So for this, what we do, we replace, because this is the definition of autocorrelation function Rx t1 t2 is equals to expectation of xt1 into xt2. Okay. So if in here I replace t1 by t and t2 by t is like this, and then it means it's the expectation of t whole square. So that is expectation of xt square is Rx t1 t2. So if you want to know what is the, if like if I give you in some problem that this is the Rx t1 t2, calculate the expectation of calculate the expectation of xt square. So what you do in Rx t1 t2, you replace t1 and t2 by t, and you will get the expectation of xt square. Similarly, you can calculate this variance also with the help of this. If so like it's in some question, I provide you this auto covariance cxt1 t2 rxt1 t2 minus mu xt1 mu xt2. So if in this you replace t1 and t2 by t, you will get so if you replace this, you will get here expectation of x. Like here, if I replace t1 and t2, then here I will get mu xt, here also mu xt, that is expectation of xt square, and here expectation of x square. So you will get the like c xt1 t2. If you want to know what is the variance of xt, that is you just replace t1 and t2 by t in the given value of autocovariance, you will get the variance of the process. This is another definition of covariance, and you remember this also. Earlier we are having expectation of x minus expectation of x, and here we are having y minus expectation of y. But here random variable are xt1 and xt2. So we are having xt1 minus expectation of xt1, xt2 minus expectation of xt2, and then we have to take whole expectation and we will get the autocovariance of the random process xt for the point time instant t1 and t2. And you earlier also we have solved this one, and after multiplying and distributing this e over them, we will get the this formula, this autocovariance, this definition. And again, when this autocovariance is zero, it means they are unrelated or independent. So if xt1 and xt2 are independent, it means their autocovariance is zero. Now this is one problem that xt is the your random process, and you have to find its autocorrelation. Okay. So autocorrelation formula is this one, rxt1 t2, and it is expectation of xt1 xt2, and then you have to substitute what is the value of xt1 and xt2. Like you know that in this question, for example 10.2, the xt is defined by a plus bt. So in this a plus bt, you replace t by t1, you will get a plus bt1, and t by t2, you will get a plus bt2. Now you multiply these two. After multiplication, you have one term a square, another term is a b1, second term is b a t2, and third term is b square t1 t2. And then after multiplication, you distribute this e to each and every term, then you will get this. As this t1 and t2 are real constants, so they will be out of this expectation. And if you remember the first lecture on this random processes, that is the previous lecture, you can say, there we have calculated if any random variable x is having n 1 distribution, then the expectation of x square is 2. So if you see the last lecture video, or if you remember, then you will get the, because a and b are following this normal 1 distribution. So being normal 1 distribution, it means their expectation is 1, and 1, and variance of x is also 1. And you know the formula, this variance of x is expectation of x square minus expectation of x whole square. And from there you can write, because it is 1 and this vx is also 1, and then this 1 goes to other side, it will give you this expectation of x square as 2. So a and b are normal and 1 so you will get expectation of a square as 2, expectation of b square as 2. Now what about this ab? Because a and b are independent, so the expectation of AB is actually product of their expectations. And since A and B are again normal 1, so expectation of A is 1 and expectation of B is also 1. So substitute all these values and you will get this. Now, once you have calculated this autocorrelation, now you have to calculate autocovariance. So autocovariance formula is denoted by this cxt1 t2, and its formula is rxt1 comma t2 minus expectation of xt1 into expectation of xt2. Actually, this is mean xt1, mu xt1, and mu xt2. So here you substitute the value of Rx T1, T2 from the this calculation, and this is the value. And what is expectation of xt1? If you remember today class only, then this for this process, its expectation of xt is actually turns out to be 1 plus t. So 1 plus t. So if t is t1, then 1 plus t1, and t is t2, then 1 plus t2. And after multiplication and simplification, you will get 1 plus t1, t2. So this is the way we calculate our autocorrelation and autocovariance for a random process xt. So we class है थोड़ा देर से. Okay, this is another problem, and this is for the discrete kind of random variable. And this problem also we discussed in yesterday last class and today class also. That 1000 rupees you have, and you have invested compoundedly with interest rate of capital R, and R is a uniform from 0.04 to 0.05. So if like before discrete, you can see that here we are having M and N. So instead of T1, T2, if you are having discrete kind of random variable, we will write Rx and N. And it is like earlier, it is expectation of xt1 comma xt2. It is like xm xm. What is xm? Xm is 1000 1 plus r raised to power m. And what is xn? 1000 plus 1 plus r raised to power m. So if I write the both of them here, then 1000 from xn, 1000 from xm, it will become 10 raised to power 6. And 1 plus r raised to power n into 1 plus r raised to power n. So if I assume 1 plus r equal to y, so it is y raised to power m into y raised to power n. And if r is uniform 0.04 to 0.05, then y is uniform 1.0.04 to 1.05. So this can be rewritten as y raised to power m plus 1, and then say uniform, it's a continuous kind of random variable, so its expectation will be calculated. This integration from this a to b, here a is 1.0.04 to 0.05. Then this density function, so density function of this y equal to 1 plus r is 1 upon 1 upon 1.05 minus 1.04, and you will get 1 upon 0.01, and which is finally equal to 100. So this is the value of density function, and then y variable raised to power n plus n. And after integration, this is the autocorrelation. Similarly, you have to write the autocovariance function also. So this is Rxmn, and this is the mean function. Mean function we today only we have calculated for this process, and this is actually turned out to be this in today's class. So here if you replace n by m one time and m another time like this, so one time for xm and xn, and this is rm xmn from this, and after simplification you will get the um, autocovariance for this kind of example. Now we talk about the multiple random processes. That is, we are having two kind of random processes. One is representing, like for example, this fuel price, and another one is representing this your gasoline price. Okay, and someone want to know how they are related, this fuel price with this gasoline price. Or if one is increasing, another one is increasing or decreasing, or they are independent. This kind of things you want to know. So that means we have two random processes. One is xt, this one, and another one is yt. And now we have to, because this xt is one random process, yt is another random process. And for any particular t1, x t1 is one random variable, and any particular value of t2, y t2 is another random variable. So we are having two random variables, and we want to know how xt1 is related to yt2. Either they are positively correlated, negatively correlated, or are they independent. So for them, we calculate the correlation. So because here we are having two random processes, so I use the word this cross correlation. So earlier this is auto because we are talking about only single process xt. Here we are having more than one, like one is xt, another one is yt, two random process. So the cross word is there. Cross correlation rxy. Earlier it is x only since we are having two random process. So rxy t1 t2, and it is defined like this x t1 y t2. So because earlier it is x, so xt1, xt2, but here rxy because it is cross correlation between the two random processes xt and yt. So its the cross correlation is defined by this. Similarly, the cross covariance is also cxy t1 comma t2, which is a covariance of xt1 comma yt2, and it is like a cross correlation minus mean of xt1 and mean of yt2. So like here we are having one random process, and here it is given that it is A, B, and C are three independent and normally distributed and one random variable. So here it is given that A, B, C are three independent and one random variable, and this xt is the random process. Xt belongs to 0 to infinity. Is a one random process is defined by this xt equals to a plus bt, where t belongs to 0 to infinity. It means it's a continuous time random process. This xt. Now we have another random process yt also with us, and it's defined like this: yt equals to a plus ct, and here it is also continuous because t is belonging to 0 to infinity. And here there is a relation between ABC. ABC are independent and they all follow the same distribution n1 1. So you have to calculate its cross correlation and cross covariance function. So because in cross correlation and in the cross covariance we require this mean function of xt and yt. So first we calculate the mean function. Mean function of xt is expectation of xt, and the value of xt is a plus bt. So you have substituted a plus bt here, and then you distribute this t on these two terms because this t is independent of t because it's a real constant. So it can be rewritten as expectation of a plus t expectation of b. And what is, because a and b are both normal and 1 1, so it is like 1 plus t. Similarly, for a plus ct, we will also get 1 plus t. So the mean function of x mu xt is also 1 plus t, and the mean function of mu yt, that is for yt process, it is also 1 plus t. Now we come to the main question like Rx T1 T2, that is the cross correlation between the xt1 and yt2. It is defined by expectation of xt1 yt2. What is the value of expectation of xt1? Because xt is a plus bt, so we replace t by t1 in the definition of x, and we replace t2 t by t2 in the definition of y. We will get this, and after multiplication we will get this. And then you have to distribute this t on each and every term. And since this t1, t2, and t1, t2 are real constants, so they will be remain out of this expectation. So you are having this. Again, since this A, B, C are following this A, B, and C are following N11, they are following this N11, and you know that if they are following N11, expectation of A square, expectation of B square, and C square is 1 because this we have calculated in earlier classes. So expectation of A square is 1. Now, what is expectation of AC? In the question, it is given that A and C are independent, so it is the product of their expectation. What is expectation of BA? That is product of their expectation. What is expectation of BC? Like this. And after substituting all these values, we are getting this one. So this is our cross correlation function for xt1 and yt2. Now cross covariance. We have already calculated this rxt1 t2 in this step and mean function in the last slide, previous slide, and we substituted all these values. And after simplification, we are getting 1. So this is the way we calculate this mean function and autocovariance, auto correlation, cross covariance, and cross correlation function. So in the next class, we will learn what is a stationary process, wide sense stationary process, strict sense stationary process. Earlier, this kind of question I used to ask in the exam when it is an offline mode. Even though I asked in online mode also some questions similar to this, to try to practice how this e expectation of e, e raised to power a square is coming, because I may play some trick here and then you may get confusing like that. So you have practice that it's not that maybe I write here n22. If I just write like here n22, then the value of this expectation of a square will change. So you listen in the previous video that is already shared in your groups, how these expectations are coming and how we are doing. Because in exam I can do like this also. No? So this class is over here, and attendance to all of you. Tomorrow I will take attendance one by one. Today I am giving to all of you. So if you have any question you can ask, or you can also leave and I can also leave. No one is asking, so please.